All right, welcome back. So in this lecture, we're going to talk about the next topic, which is MMD, kernel main embedding, and HSEC. So yeah, I'm Professor Wu. Let's get started. So we previously learned kernel divergence. So that was from information theory, and kernel divergence idea is basically you have two distributions like this one and this one. And kernel divergence is a way of measuring the difference between the distribution. So if the distance between them is very large, then the kernel divergence will be KL divergence will be large, and if they are small, the value will be small, and KL divergence will essentially be zero if the two distributions are identical. So so these are KL divergence is essentially a way to measure how different the distributions are, right? So over here you can see KL divergence between red and blue should be a small value because they are similar. KL divergence between red and green, on the other hand, should be a large value because they're quite different. So now, if we only have the data, so KL divergence has some disadvantages. One is that if we only have the data, then we essentially need to get P of X and Q of X. Okay, so if this is P of X, the red, and Q of X is this one, we essentially need to, if we have the data, we need to identify the distribution first, P of X, Q of X. And, there's some loss in there if you do that you may not always be able to get a really good representation of the probability distribution. So that could be annoying. And for continuous distributions, we would need to solve this complicated integral as well. And calculating this integral is doable, but it could get kind of annoying. So you have to do this, identify distribution, then you have to solve integral, and then finally, once you solve the integral, then you would have the value. Moreover, so far doing this in just one dimension data, right? Just one dimension, it's easy. But you can imagine, how do we do this KL divergence when we have more than one dimension? Well, we will end up having to have multiple integrals, right? So we have to solve a much more complicated integral. So these are all the disadvantages of KL divergence, even though it is useful. Now, instead of KL divergence, there's another method called maximum mean discrepancy. This was invented by a professor at UCL. His name is Arthur Gritton, and for so you can look at the table here. KL divergence. You take the data. You need to know the probability distribution. Then you have to solve integral. Then you finally get the distance between the two distributions. However, with maximum mean discrepancy, you take the data and you just directly calculate the distance. And this is a much direct way and simpler to do it. Moreover, with MMD, even if you have higher dimensional data, you can still do it. So this is actually pretty useful when you move on to more complicated data. So the maximum mean discrepancy. Okay, let's assume we collect n samples, right? And we're going to call that distribution P of X. So that we know that X is a snapshot of P. Next, the way it works is that we map every single point into RKHS. So from our previous lectures, you know how we have a space. So this is the data space. And then here is the function space. KHS. Every single point can be mapped here via the feature map, right? So this is 5xi, this is xi. So this point here is the equivalent point. So you can imagine if we have multiple points, and we map every one of them here, so we have multiple points. So if we collect n samples, right, n samples, and we map all of the n samples here, well, there's going to be a cloud, and among that cloud, you're going to have an average point, the middle point. Well, the middle point is also a point inside RKHS. Therefore, this middle point is a function. Function, right? Now, we know that every single point is a function that came from a data point. But this middle function, which I'm going to call it mu function, doesn't have any meaning. I take a second. This is also a function, right? But does this function have any special meaning? And the answer is yes, it does have a special meaning. And the special meaning, this first of all, this function, the average point among all the points in RHS is called the kernel mean embedding. So that's the name, kernel mean embedding. And this function happens to be the probability distribution times some kind of constant. So this time just a number is equal to the probability distribution. Okay, you can think of it that way. It's really a representation, but in depending on the kernel, you can just view it as equivalent. Okay, so now this means that we can find this p of x multiple ways. Previously, we learned one way is just to recognize the shape of the data, right? This is a Gaussian, this is an exponential. So that was how we recognized it before. And then we learned this technique called maximum likelihood. We also learned a technique called KDE. And now we know that all we have to do is find the average point of the function RHS. So the question is, how is this possible? Like what is the intuition to that the average point, which is a function, happens to be basically the probability distribution, like times some constant. So let's try to gain an intuition of how this works. Previously, we have learned this technique called kernel mean embedding, right? So the way it works is that in kernel mean embedding, you take every single sample, right? Let's say you have multiple samples. You take every single sample, and you put a Gaussian around that, and another sample, you put another Gaussian, and you just keep adding Gaussian distributions centered around your data, and that will create your ultimate distribution, right? So it's saying that the probability distribution, according to KDE, is a summation of multiple Gaussian distributions. So these are all Gaussian, with center at the points. This is x1, x2, x3. These are the sample values, x1, x2, x3, and they are used as the center. So whenever we want to find the probability of an event, all we have to do is plug x here, which is here, here, essentially for every single sample, right? And once we plug that in, divided by n, then we would essentially have the probability distribution. So hopefully you remember this from the KDE lecture. Now, so this is saying that the equation for the probability distribution is equal to the summation of Gaussians. Right? And now notice how the constants are the same. So we could just move that outside. So let's move it outside. So every one of these is what was inside. Now remember the definition of a Gaussian kernel. The Gaussian kernel is equivalent to this. Notice how this looks equivalent to the inner part, the exponents of the Gaussian distribution. So this means that this right here is xi xj. So this is equivalent to a kernel function. What that means is we can replace all of these with a kernel function, so that we still plug x in here, but here's x1, x2, x3, all the way to xn. So this is equivalent, right? It's just based on definition. Now, the kernel function is the inner product between the two samples inside RKHs. So we take the inner product. So let's write that down. So this is the inner product between x and x1, right? X, x1. This one is x and x2. This one is x, x3, x, xn. So these are the inner product. And for all these inner product, you also notice that phi are all the same. So we can pull that outside again. So let's pull that out. So after we pull that out, I'm going to move the n here. So 1 over n was here. I'm just moving it because it's a constant. Notice how this, after you pull out phi of x, this is just the summation of all the samples divided by n. This is the average point. So this right here is the average point, right? So if this is the average point mu and times phi x transpose, this right here is a function, which is mu of x. And notice how mu of x multiplied by a constant c is mathematically equivalent to p of x. Right. So that's why you can see that if you simply add up all your points inside RKHS divided by n, which will give you the average point, this is equivalent to a function, and this function is equal to mu. And this mu has a direct connection to the probability distribution itself. Okay? So this is how you can understand why p of why the average point can be treated as a probability distribution. Okay. Now, picking the Gaussian kernel, right, which is what we did in this example, Gaussian kernel, you can see that this will obviously work. It will work like with KDE because that's how KDE does it. But besides Gaussian distribution, which looks like this, there are many other distributions you can pick. There's one called exponential, which is sharper. There's one called Maton. I think it's fatter. I don't remember. But the point is that you can pick and choose many different kernel. However, you can't just pick any kernel, any random kernel. Not all kernels will work, right? Like some kernels will not work. And that's because, like mathematically speaking, for some kernels, it is possible for two different distributions to accidentally have the same center point. So if you have one distribution, if you use some kernel, one distribution, another distribution, they're different, but you can accidentally have the identical point in RKHS. And that would not be good because different distributions should not yield the same point, right? Because the whole point of this is that it will be different for every single point. So this tells you that like not all the kernels will definitely guarantee that the point you get is a distinct probability distribution. So because of that, then you can't just pick any kernel, right? So us researchers, we basically figure out exactly which set of kernels you can pick and which criteria you will have to satisfy. And we call these set of kernels characteristic kernels. So essentially, as long as you stick with characteristic kernels, you can always treat the average point, right, in RKHS as as basically a surrogate for the P of X. Okay, and Gaussian is the most common one. Hence, when we use kernel density estimation, we use Gaussian. But you can also use Laplacian, Mattern, etc. Like there are lots of characteristic kernels. Okay, so the point is, as long as you stick with the characteristic kernels, the kernel mean embedding can be interpreted as like the probability distribution scaled. Viewing the function p of x as a point in RKHS has a major advantage, right? So now this point is a function, but this function has a very specific meaning. If we view this as a p of x, this means that if you have 2 points, they're essentially p of x, p of y. You have two distributions. You can directly measure the distance between them in this space with the L2 norm. Right? You can picture just basically literally measuring the distance between two vectors. So this therefore we can use the L2 norm to measure them. So if this is the center point for x and this is the center point for y, the difference between them and the magnitude of that give us what we call the MMD. MMD is the second way to measure distance between distributions, and it's a much better way, in my opinion, than KO divergence. I like it so much more than KO divergence. And that's not because I have preference over Arthur Gretton's work. Okay. So to calculate MMD, you can. So far we've gone through random Fourier feature, and the Mercer theorem also tells us that the phi of x is equivalent to the eigenvectors, right? Eigenvectors. So you can represent these vectors, I mean these points in RKHS as vectors, non-infinite, finite vectors which you can calculate, and you just subtract the distance, and that's it. That's really really simple. However, traditionally we do not use RFF in this because there's actually a kernel trick to which you can calculate it. So let's go over the kernel trick. So over here, remember this is the average point for x and average point for y, which means that how do you find the average point? Well, if you take the average point, if you take phi x1, phi x2, phi x3, so on and so forth, these are every single phi, right? Now, if you multiply by the vector 1, then it's going to add them together. So this right here is phi transpose times the vector 1. This is how we get phi transpose times vector 1. And if you divide it by n, then you're going to find the average point. So this right here is equivalent to this. And similar idea, you can just average all the points divided by m if it has m points. So, and then we take the square. So the square is simply this times the self transposed. And okay, so now if we multiply them together, we actually do every combination of the multiplication. We do every combination, then this right here, that we're going to yield this, and then the y's are going to multiply together, and then the xy terms we're going to end up with two of them. So these are the xy, these are the yy, these are the xx. So we end up having four terms, two of which are combined. Now, this right here, from the other kernel lectures, this is just the kernel matrix for x, right? And this is just the kernel matrix for y. And this is the kernel matrix for x, y, right? So if you have, right, phi of y, phi of x transpose, that essentially give us this. So I'm just going to call these kx, ky, kxy. Now, what do you think the ones are doing here when we multiply them together? Well, let's see. If we have a matrix, like this one, 1, 1, 2, 0, and we multiply ones, what do you think is happening? Well, let's not do it this way. Let's do A, B, C, D. All right. Okay, let's just see what happens. What does it do when we multiply them together? So it's A plus B, C plus D times 1, 1, which give us A plus B plus C plus D. Okay? So what it's saying is that when you put two ones around, you're essentially adding every element of the kernel together. So you're just adding everything together. Divided by n squared. So n squared here will be 4 because it's 2 by 2. So what this is saying is you find the kernel matrix for k and essentially find the average value. So if you have all the kernel values here, you find the average one, then that's your first term. And then similarly here, you're essentially adding all the value, and that's your second one. All the values from y, and then average it together. Similar idea. Here, if you get the kernel xy, and you then average them together, times 2. Okay? So this right here would yield the average for kernel x, average for y, and 2 times the average for xy. This is essentially the equation. So if you just calculate the kernel for x, xy, and then kxy, then their average points add up together. It will allow you to calculate MMD. Okay, so let's continue. I wrote the code for you over here. Over here is an example of MMD where you have three distributions: red, blue, and green, right? And if you calculate it, notice how the distance between red and blue is small, but the distance between red and green is much larger. So, this is essentially a way to spit out the distance between distributions, and you can have higher dimensional data. Okay. Now, I want you to basically take a second to reinforce everything you learned. Go back to the previous slide and go over the derivation. If a particular step doesn't make sense to you, make sure you have the TAs explain to you. And then once you understand that derivation, see if you can reproduce it yourself. Think about the steps we went through and see if you can reproduce the logic behind how everything happened, and then such that it leads us to this final equation. Okay, so we're about to do multiple algorithms now based on MMD. So pause the video, make sure you can do this, and then we'll move on. Okay. All right, so with MMD, there are many applications. One of which is called subsampling. So let's say you have 1 billion samples, right? If you have 1 billion samples and you need to run any kind of algorithm on this, it will take a really long time because, well, you have 1 billion samples. And very often, you don't need the entire 1 billion samples to run your entire algorithm. Instead, what you can do is to pick a subset of the samples. And this subset maybe is only 100,000, right? 100,000 is still a big number, but much smaller than 1 billion. Maybe just by using 100,000 samples, it's good enough. So MMD is a way to help you essentially pick this 100,000 samples. What you can do is you can essentially identify, let's see, what you can do is essentially identify the distribution of the total, so P of X, and then identify the distribution of the subset. And we're going to call this P hat of X. So this is the total population. This right here is the subset. And if you simply pick a subset, I don't know, let's start with 500 samples, right? So if you do 500 samples, you're going to get some kind of distance. And then if you increase 500 to 1,000, you're going to get another distance. You increase it to 3,000, you're going to get a distance. You can imagine that as you increase this little by little, the MMD between the two distributions are going to get smaller and smaller, which is shown here. Right? As you use more and more samples, the distance between them are going to be smaller, which implies that even though maybe you have 10,000 samples here, right? Maybe you only have 10,000 samples. Yet the probability distribution between your 10,000 samples and 1 billion is basically the same. So if the distribution is the same, if you need to run inferences based on the distribution, then maybe you don't need 1 billion samples. Just the 10,000 is good enough. Okay, so you can see how by using MMD you can keep measuring the distance between the two. Now, if you have 1 billion samples, finding the kernel matrix of this will be very hard. So maybe instead of comparing the total to the subset, what you could do is you simply have to pick a subset, right? And we're going to call this subset Q of X. And then we pick a bigger subset, which would be Q0 of X, Q1 of X. Okay? So now what you can do is you can measure the distance between Q0 and Q1. And then you do this again by expanding it and measure the distance between Q1 and Q2, right? And then you can measure the distance between Q2 and Q3. Each time you're increasing the size. By doing this, maybe you can just see that the distance is no longer changing. In other words, as you increase the number of total samples, right? Every single increment is maybe gets to a point that it no longer changes the distribution, right? So the change in distribution can get less and less and less, such that when you add an extra amount extra amount of samples, this extra amount, you're not improving the distance anymore. So you can also do it that way. And this would, in some cases, able to save you a lot of computational time. Okay. Okay, so next, so that's subsampling. So this right here is an example. I basically have a 60,000 sample. This is quite a bit. And then when I use this idea with an MMD, essentially I can achieve almost equivalent distribution. Like the two distributions are very, very similar with just 150 samples. And you will much rather be running algorithms on 150 rather than 60,000. And you can visually see that is a reasonable representation of the original data. Okay, so that's one application for MMD. Another application is for classification. So let's say you have three clusters. So these are the different data set. So what happens if you simply take each cluster? Let's say you know the label, right? You take each cluster and find the p of x for the p of p1 of x for this one, p2 of x for this one, p3 of x, right? So now if you get another point, let's say another point here, you simply have to plug this point into each one of them. Like uh, So what you want to know is you want to know the probability that um, let's see, the probability that a point x is in the probability that x is in uh, p1, right? So if you know the x, you can just plug x into each and every one of them, and then whichever gives you the highest probability, then you can say this point belongs to this cluster. So this essentially allows you to do classification. Okay. Okay. Now let's continue. Anomaly detection. So this is for this particular example, like as long as you can detect the data during normal operations, you can model the P of X. Once you have P of X, given new data, you can measure the distance between the new point and your embedding, the center point. If the distance is too far, then you treat it as an anomaly. So let's say, like, I think I gave you guys an example where in autism, for kids with autism, there are people doing research to put wristbands that measure their bio sensor data, and the goal is to detect anomaly. And once they detect anomaly, they will be able to say, well, this kid is about to get triggered, it might get violent, and you want to intervene. So so that's an example perfect for MMD, right? If you want to detect something strange is about to happen, all you have to do is figure out the center point. And if the distance between the new point and the center point gets too far away, you can say that okay, this has deviated too far from the original. And if it has deviated too far from the original, then you can raise a flag saying this is anomaly because it's too far from the probability distribution. And you can use the same idea for a bunch of things like credit card fraud detection, right? So if you always buy things in the morning and you always buy them in a like certain state in certain city, and then suddenly you buy something that's really far away in Bangladesh, for example, then they can raise that as a flag and say something doesn't seem right, right? Fraud detection, like the one for health conditions, maybe you can detect um, like heart rate, like that is out of ordinary, or if a heart attack is about to happen, or you can detect attacks from hackers, right, by observing internet traffic. Like you have a probability distribution for a normal traffic, and then suddenly something out of the ordinary happens, and you can catch stuff like that, or catching terrorist attacks, right, by modeling their network communication, or you want to catch critical battery failure for airplanes and cars, right, before they crash, or you can catch drunk driving. So basically, anything out of the ordinary, you can essentially use this technique to help you catch it. So MMD is quite useful technique. Now, MMD can also be used for generative models. So you can imagine, you can imagine that if we have data, and this data set are data sets of people's faces, right? Of people. And therefore, one sample is a picture of a face. So every time you get a sample, you got a picture of a face. And from this, we can get the probability distribution of it. So we have the data, and we can somehow find the probability distribution of the data. From this, you can imagine if we were to get a sample here, then one sample will also be a picture of a person's face. Now you can imagine what happens if we, let's say, generate sample from a Gaussian distribution, X. So we just random. This is completely random. Random. We pass this through, we pass this data through a function such that it gives us Z. Okay. And from Z, there's, it has a distribution as well, Z, right? What do you think happens if we were to minimize the MMD between P of Z and P of Y? Okay. You want to take a second and think about what happens here. So, so here we just mentioned this is a probability distribution of people's faces. Therefore, if you get one sample, of this, then that sample will be a picture of a person's face. Over here, if you were to minimize this MND such that they're mathematically equivalent, then this must be a distribution of people's faces, right? If you find a function such that you take a sample and you pass it through the function, that gives you one single sample, then this right here is a picture of a person's face. So you can imagine MMD can also be used to generate different kind of data. And indeed, there's an algorithm that used this general idea. Not exactly the same, but the base idea with this. And they were able to generate the first generation of pictures. Now, they're not amazing, because this was like the first generation. But you get the idea. Nowadays, we can generate pictures like these. None of these people exist, and yet look at the picture quality. Like it's pretty incredible how much they've advanced. But you get the point. You can use MMD to even do things like this as well. So so I think this is it for part one, the MMD lecture. In part two, I think we're going to talk about another concept called the Hilbert-Schmidt independence criteria, or HSIC. So in that case, I'll see you in the next part two of this lecture.